We were asked to create a new sound design for a 1,500 seat performing arts center. Currently, there is an audio system in place. It's very old. It's a center channel of point source speakers. I'll probably put a picture right here. The the audio system is very limiting in the types of content that the municipal theater can host. In addition, this theater is used on a daily or weekly basis for education purposes for students. They don't have a very modern or functional system to learn about performing arts, learn about audiovisual technology. This venue is somewhat narrow and relatively long. I think the furthest seat from the stage is somewhere around 115, 120 feet on this y-axis. And the proscenium is rather short. And there's a whole bunch of features that don't create a clean surface for us to mount a frontal audio system to. And additionally, we have these two catwalks, and these are really a bit unusual and also a bit limiting, to be honest. So given some of these constraints, we wanted to create a sound design that was still effective, with the goal being to have a professional level audio experience in virtually every seat in the auditorium, all 1,500 seats. What we did at this point is we want to start off with creating the frontal scene, because we know we're going to need that. So to begin, based on the experience using products like L Acoustics, we felt that the A-series would be a good place to start. There are some smaller variable source line arrays like in their K-series that might also be a fit, but based on some of the budget constraints that we were looking at, it seemed like the A-series constant curvature line arrays were probably going to be the sweet spot for performance and value. So we first take a look at a position. We may start off with a traditional left and right. You want a stereo image in most live performance venues, and in theater and in performing arts, there may also be a third center channel. We'll talk about that in a couple of minutes. We want to first take a look at our left and right, and those are typically symmetrical. We put up a line array, and the first thing that we'll do is check the angles, in the horizontal plane. Like, what are we aiming at, right? Are we aiming at people? Are we aiming at walls? Is there any audience there? So on and so forth. We'll get some line arrays up. We'll mirror them so they sort of track each other. We can make adjustments to these line arrays, both in their location and also the angle. And then there are a couple tools located within this program, Soundvision, that make this actually super easy. This is our source. Before we take a look at the vertical coverage in a 2D cut, we want to take a look again, like, what are we aiming at, and are we generally happy with it? These two lines coming off of the source are actually the pattern sort of in a horizontal plane that we're dispersing the sound energy. Within the program, we can make some changes based on the capabilities of the loudspeaker. And one of the reasons that we chose the A-series loudspeaker is because it has a feature that allows you to narrow or widen, both symmetrically and asymmetrically, the sound dispersion. Literally a couple of fins on it will steer where the sound goes. And this is really important because we want to keep sound where it's wanted and not where it's not wanted. Okay, so we've got the radius of impact points going on over here. You can see all these circles that you may be noticing on screen. These are our impact radiuses, meaning imagine sound energy, sound pressure is coming out of these loudspeakers and it's hitting things. What you might notice here in both of these screens, here and then again here, this arc goes way beyond the wall, right? And we can see, look at all this hot orange, yellow energy. Look at that. What good is that going to do? All that's going to do is create a bunch of reflections in the room or necessitate a ton of sound treatment on those walls. And is that necessary? Is that good? I like what's happening from the stage position, the left side. We have a lot of coverage here. What happens if we, say, turn these arrays? Okay. Now, we've actually increased the energy on that wall and we've decreased the energy in the audience. Well, that's not very good, right? And then what if we pan all the way across? Well, that looks pretty good, but now we're actually leaving some of the people over here high and dry. They're really not going to hear anything. And the only source of sound that they'll hear is all the way on the other side. I don't think we really want to do that. Let's use those adjustable fins that we talked about. My goal is to retain what's happening on the left side of here, but reduce this crazy energy buildup on the sidewall. We don't want that. So let's go and close half of those fins. And what we can see here, both here and here, is that we really closed off the energy moving in that direction. And immediately we can see a drastic reduction, huge reduction in the energy that's actually hitting this sidewall. Now that we've really reduced some of the energy off the sidewalls, we can probably think about moving on at this point. At this point, we may want to, reposition these elements a little bit and sort of play with the overall sound pressure that we're getting. Maybe we'll move them in just ever so slightly and turn them out just a little bit. This is starting to look pretty favorable. Now that we have this piece done, we could take a look at the 2D cut view, but on the vertical plane. Okay, so now that we're taking a look at the 2D cut view on the vertical plane, there are some immediate things that are limiting, like we talked about before. Here's our line array, right? You can see that here. This is the 2D profile. And right now, the top of it is parallel with sort of the floor and the ceiling. It's at what we can reference as a 0 degree sight angle. And we can change that. We could tilt it up, we could tilt it down. Right now, we're able to achieve about 2/3 of coverage. What about the rest of the audience? Well, after looking at this design and the space constraints, we didn't believe that it was feasible to achieve total coverage with the frontal array. And that's because of two major factors that we discussed at the beginning. One, if we could get the line arrays higher, we might be able to achieve that. The proscenium is directly above this line array. And to get it any higher, we would have to drag it up here to make some room. But then guess what's going to happen? We are shooting directly into that catwalk, and that's not going to be good. Two, even if we bring it up that high, now we're not covering the front few audience rows very well at all. Let's bring it back to where it was. At this point, we are, I don't want to say settling, but we've said, okay, let's cover the first 2/3 of the audience and let's do the best possible job at that. And we'll come up with another solution to cover the last third and try to give them a consistent experience. Now that we are pretty happy with the overall angles of the arrays, how they're being configured, what the variable coverage is doing, the integrity of the SPL from front to back with the primary array, I want to talk about a key element that we have to add because we're talking about a performing arts theater here, and that is a center array. Why is this important? Typically with performing arts, there are performers and there are actors that will be front and center on stage. When you have a stereo image, the sound will be bigger and wider, which is great for music and effects. But when you're in the audience and you're watching a performer at center stage, you don't really want to hear them around you. You want to hear them where they're speaking from. And if they're typically in the center of the stage, you're going to want to hear them in a very kind of more direct and narrow targeted way. And so mixing engineers will typically take the stems or the mics from the performers, the actors, and whoever else is in monologue or in a lead position. They'll mix that to this center line array. It will prevent a cognitive dissonance scenario where you're hearing people all around you, you're hearing the actor around you, but you can see them right there at the center. And that's really important to prevent frustration for the audience. Now that we've got our frontal scene, let's talk about and let's look at its limitations and how we're going to bring in a solution. We've got our frontal arrays here. a lot of impact points going on at the front, especially now that we've added that center channel in. And as we move up into the second tier here, they get more sparse, they move away from each other, and they eventually turn green. And if we look over here on our chart, we're making our way down from 100 dB and towards like 95 dB, maybe even 90 dB territory. And then they all together stop at the end. So you can see here, we've now fully mapped the area. And a couple of things come to mind when we see this. One, of course, is, as we mentioned, in the area of primary coverage, we have a lot of yellow. So what we're seeing here is in dBA, we have a big drop off. In fact, we have like a shadow in the back, and that's not good. We can't have any shadow. Where there's an audience member, we can't have any shadow at all. We also see a little bit of this in the front. So these are the two things that we definitely need to address. We need this yellow to be everywhere that there's audience, which includes this entire area. This whole thing needs to be yellow, and we can't have any shadows at all. We like the pressure level and the tonality of our 3-line arrays in the front. We want to keep that experience going to the top third of the audience as well. That way there's no bad seat from an audio perspective in the entire place. So to do this, we add what are called delays. We added 6 more boxes, the same ones that are at the front, L-Acoustics A-series. Now, just like the primary array, we can go through that process of orienting them to reduce sidewall reflections, to ensure that there's overlap coverage, to ensure that there's enough SPL. We start to roll off coverage as we approach probe 8 with those open circles, but we haven't made our way into green yet. And then when we go back to our delay, that's exactly where we're rolling coverage on. And so this mesh point is really critical. And by placing our arrays where we've placed them and angling them in a way, we're able to achieve that coverage that we're lacking. So not only do we want to ensure that we have coverage beginning somewhere around probe 8, we also want to reduce throwing sound all over the back wall unnecessarily. We want to reduce throwing sound all over the sidewalls. And again, this is to keep the audio clean. This is to reduce reflections. This is to reduce muddiness or too much noise or sort of almost what can lead to a fatiguing acoustic environment. To do this again, we can go back to our 2D cut source. And these arrays, unlike the ones in the front, we did not have them at that 0-degree sight angle. We lowered them, and we did this for a reason. We did this to reduce impact off the back wall. If we were to have this angle be 0 straight across, we would send energy all over that back wall. We only need sound pressure where there will be audience members. In this area here, truly represents the last row of seating. We lowered the sight angle by about 6 degrees to extend our coverage down towards probe 8 and to remove rear wall reflections. Let's take a look at how we're doing. The picture is looking way better. The back, we've almost entirely solved this issue, all right, which is excellent. We still have more work to do, and that is up here in these corners. And luckily, the solution is pretty simple. We add what we call front fills. And in this case, we use a series of 5XT point sources basically along the front lip of the stage. What you'll see here is that with these front fills, we immediately solve that final issue. The shadows are completely gone, and we have what we're after, which is a uniform consistency from front to back. Now, the final piece of this, as we mentioned before, whether it's theater, performing arts, or concert, you want to have some impact. You want to have some low-end punch for effects, for drums, for musicals. We added a center cluster of KS21 install version, KS21i, which pair perfectly with our A15 full range loudspeakers. Now, we did have a couple of choices to make. First, when you have subwoofers spread apart, they can really create a lot of problems. And I'm not going to get into that in this video as far as the nodes and the cancellation and the summation of subwoofers. That's probably best in a separate video. We have a center cluster of KS21i here, and we'd fit as much as we could. As you can see, it's very tight there, and rigging it will be, maybe not so fun, but this is really the most that we could get away with. If we added any more boxes, it would impede upon the sight lines. It's just not an option. We had 6 boxes max that we could work with. The major choice at this point is whether or not we want to use some type of steerability. In this case, we decided that we did want to use steerability. As you may notice, one of these boxes is turned around on both of these arrays. This is what's known as a cardioid configuration, and L Acoustics recommends 1 out of 3 or 1 out of 4 of these boxes to be in reverse. And they have a preset which will electronically delay and in some cases reverse polarity on the electrical signals inside the boxes to create a directional output of those subwoofers. We have a very clear delineation between the sound pressure levels. 6 dB per color step, meaning that we're at a total of 12 dB in difference between the people right in the front and even at the front of the stage and at the back. And that is not ideal. Why? Because A, your audience is having a very different experience. The people in the front are getting kind of blasted with subwoofer, which some of them may like that, some of them may hate that, but overall they may not be able to hear other content. It'll be overwhelming. And then the people in the back are not getting enough sub. And if you try to increase the low for the people in the back, the people in the front will be like leaving the theater. They'll be running for the exits. Additionally, we have a lot of low frequency energy on the stage. And this can be really problematic for actors and performers. So there's techniques that we can do to mitigate this lack of consistency in the audience and also the buildup of low frequency energy on the stage. And so to do this, we will typically utilize a cardioid configuration. So if you remember before, this whole area was super red and we had a bunch of red on stage and then we had yellow in the back. So immediately, this is a big improvement. Why? Less people are going to be getting blasted by subwoofer in the front, and the people on stage are going to be getting considerably less subwoofer, up to 6 dB less subwoofer. So they'll hear like approximately half the amount of low frequency on stage. The people in the back are as they were before. The key here is that the difference between the front and the back is much smaller. Let's try one more option. Let's try the CX preset. We have a major difference. We have no more red whatsoever. So you can see that this preset results in definitely some overall peak output sacrifice here. No one's getting blasted anymore. The stage is very quiet. We now have green on stage and we have some yellow, and there's really no energy there. And overall, we still have yellow in the back. So which of these options is right for this space? We don't exactly know. In my opinion, the cardioid option is definitely right. Is it the C? Is it the CX? Is it something custom? We don't know yet. But the great thing about that is that when we put the subwoofers up into the proscenium, this is a simple change that can be made on a computer. All right, so we've got this taken care of to a degree. What might be interesting is to keep it at this. And now at this point, what we really want to do is we want to look at the total picture. We've got all these different elements. They've all been adjusted. They've all been tweaked. What does this whole thing look like together? And the way that we do this is to look at all of these weird pyramid probes that you've been probably asking yourself, what the heck are those? So what we're looking at is the full frequency spectrum that humans can hear. And then what you can see here is that there's this sort of line. And what this line represents is the desired pressure level along that frequency response. You want your highs down to about 1,000 hertz, which you can Google what does 1,000 hertz frequency sound like and get an idea. And then humans like, as you go down from 1,000 hertz, generally for the level to increase, as you get lower and lower. We have a better tolerance for low frequency sounds. We like the energy. It doesn't hurt our ears so much. Since this is a performing arts center and theater, there's really no need for this to be above 100 dB. So we're going to set our slope pivot here at 100. We are going to set our low frequency cutoff. If we were doing EDM or techno or a rock concert, we might choose a low frequency cutoff of 32, but because we're doing more performing arts and theater, 40 should be plenty. We have our guy right here, front center. If we mute every other here, we'll only get what that person's hearing at that given frequency with those given loudspeakers. So for example, let's turn on the PA. Okay, so we can see here with probe number 1, we have plenty of level sort of across the frequency spectrum. We have maybe too much low end right in the front, and we talked about how, the subwoofer, I guess, preset may impact that. You can see after moving to super cardioid, we lowered some of that, but we still definitely have some buildup here, kind of around 80 hertz. And again, that might be something that just comes out in the mix that the mixing engineer can work with. Let's add in sort of all the lines, and we could talk about the average curve. We've added probes all over the audience. We've added them to one side in particular. Actually, this one over here has escaped me a little bit. Let's move it back. And we want to add them to one side in particular because we have symmetry in this design, and there's really no need to measure both sides. In a real scenario, once this PA is up, we would go about using probably a P1 processor from L-Acoustics or Smart if you're using another brand to time align everything and to use a transfer function to compare what the content's doing, what the loudspeakers are doing to ensure that it is as transparent as possible. This is done with just one side because the point is in a venue like this, you have symmetry. The left should sound just like the right. The loudspeakers are in the same positions. The subwoofers are in the same positions. You should have the same experience sitting on the right as you do on the left. So what we can see here is with these probes all over the place, this black average curve, this is our average. And this is looking great. We want this average to be between these two dotted lines and track as closely as possible to the center line. And thus far, we have that. This concludes the first part of this, why we chose the loudspeakers we chose, what height that we hung them at, what angles, why we needed delays, so on and so forth. In another video, we can review some of the electronics and the signal chain for a setup like this, why we might choose to run this over networked audio versus analog audio, how many amplifiers we would use, where we would have those mixing positions and have everything work in concert so that you have a professional audio grid set up in this 1500 seat theater. Thanks for watching. Take care. See you on the next one. Bye.